Army Research Lab. And she's going to talk about something I'm very intrigued, is topological quantum photonics.
All right, great, thank you. Thanks to the organizers for the invitation. It's great to be over here. I've never been to Bristol before, so it's a lot of fun. So I am at the US Army Research Lab, as this says, but this experiment is a collaboration with the group of Mohammed Hafezi, who is at the University of Maryland and the Joint Quantum Institute, which is actually just down the road. So all this experimental work is happening there. So just to start with, because we are a quantum and more of an optics community, topological systems. So topological systems have been important in physics for maybe 30, 40 years. In general, when we talk about topological systems, what we mean are systems that have some behavior which is due to some global feature that isn't affected by a local perturbation. So the kind of canonical picture of what is topology is I make a bunch of things and they're all the same topologically until I put a hole in them, and then they're all the same again topologically until I put another hole in them, and so on and so forth. So a ball is the same as a water glass, and a donut is the same as a coffee cup, but what matters is the global properties, not any kind of local change in them. For purposes here, today, one of the major consequences that occurs in a lot of topological systems are these surface states. So with topological systems, you can often get propagation or conductance to occur at the surface or edge of a material where it won't happen in the bulk. And these are due not to some, again, local properties of the system that live at the edge, but to some global properties of the system and are thus much more robust to any kind of local disorder or local defects. I'm going to talk a lot more about this. But one reason that you should know that topological systems are important in physics is because the Nobel Prize in Physics was given for them just a couple of years ago. So these guys won for their work that was mostly in kind of the 70s and the 80s. And they were really talking about electronic systems. So quantum Hall systems, topological insulators, superconductors, other stuff that I don't know anything about because I don't really work with electronic systems very often. But that's where topological physics mostly lived until maybe 10 years ago. Nope. There we go. This thing's touchy. When people started looking into moving into the photonic realm. So both in the microwave and in the optical, it turns out you can design systems that have these similar sorts of topological properties. And you'll notice that these things, which are supposed to, they're either pictures or cartoons of all of these different topological systems, they look very, very different. So people went down a lot of very different pathways in attempting to make photonic topological systems. All this stuff, if you're curious, is in this review, which I think will someday come out in Reviews of Modern Physics. It's been in the archive for a while now. But one thing that you'll notice about all of these, and it's not obvious maybe from this one, but it is in there, is a kind of lattice structure. So a regular ordering that's happening in the system, and it turns out that this is kind of a common feature in a lot of these systems, is the way that they derive their topological properties is you make some kind of a lattice and then you do something to it that gives you some global properties of the system because of what's happening in the band structure. So I'm going to explain our system, which requires starting off with reminding you all how the quantum Hall effect works. And then I'm going to talk a little bit about four-wave mixing in silicon and how we then go about generating single photon pairs in a topological mode of a chip that we design. Okay, quantum Hall effect. So everybody learned this, but everyone knows that at low temperature and high magnetic field, the current, the Hall resistivity in a system gets quantized. It gets quantized so well, in fact, it's an electrical standard. And this is due to the fact that all of the currents in the bulk of your 2D system, for your quantum Hall system, they all cancel, but the currents on the edge don't cancel. This is where you get all the current coming in these robust edge states. It ends up quantized like this, the resistivity does, and more importantly, these edge currents here are robust with respect to defects. So I can kind of poke the material and the current will go around whatever I've put in there up to a point, right? This is one thing that's well known about the quantum Hall effect. This is partially why this quantization is so clean and so nice, is the robustness of these edge states. Because, again, it's that you're not getting current on the edge due to some local property at the edge of the material, you're getting current on the edge because of some global property of the whole system. So one way to describe the quantum Hall effect is this lattice model. We assume that we've got a bunch of sites, and they're coupled by little links, and we can imagine tunneling from site to site in either of our two dimensions. If we put a magnetic field on this system, then we know that for electrons, we better get a phase when we run around in a circle, because that's how electrons work. And that's going to look in our tunneling as something that looks like this, a factor that where you pick up a phase tunneling right to left versus left to right, and the amount better vary as you go vertically. So we're going to do all this in the Landau gauge because it just makes it easier. So when you tunnel horizontally, you pick up a phase, and the amount of phase depends on your position vertically. And that means that as you go around in this loop, you pick up no phase on these lines, but you pick up y phi phase here, and then y plus 1 phi phase there, one with a plus and one with a minus sign, and that gives you phi when you go around in a circle. Fine. There's the Hamiltonian. I'm not a theorist, but so there are a couple of Hamiltonians. You don't really need to look at them. Okay. What if we want to map this onto a system of light? What are our little nodes and tunnel links going to be for light? Well, a ring resonator kind of looks like something where light can live in it, and it can tunnel out in kind of 4 ways. It's got kind of 4 ports. That looks a lot like the little links little dots with the links that I had in the last slide. And if I do this, I can imagine having, there we go. I can imagine having tunneling along this way between these ring resonators and along this way between these ring resonators, and I can write down a Hamiltonian that looks the same except for the phase. Okay, fine. I can control these tunneling by how close I make my ring resonators on my fabricated chip and so on and so forth, so that's okay. But how am I going to put a phase on? Because if I put a magnetic field through this, the light doesn't care. I'm not going to get a phase. Okay, but we know how to put a phase on light. We either change the index of refraction or we change the path length. So what we're going to, nope, that went too fast. Nope. Okay. So I gave it away. But instead of just having 2 rings right next to each other that directly hop from one to another, we put a link waveguide in. I'm not even going to call it a resonator. I'm going to try not to call it a resonator because we're not actually asking the light to ever live in here the way that we want it to be circulating in these guys. It's just controlling the tunneling from one site to another. And if we move it a little bit, which it did before, the pathway going over the top and the pathway going under the bottom are different. I didn't press start. Okay. There we go. So the pathway over the top and the pathway going around the bottom are going to be different. We can set that difference by phi. And if we do the following, where we make these links offset by some integer multiple as we run up our 2D array, we're going to pick up this phase of phi when we run around in a circle in our rings. So now our Hamiltonian, our Hamiltonian is exactly the same as what it was for the quantum Hall effect. And so we should get all the same physics now. All we've done is move these guys, and you'll see that they're not moved in this direction. They're still there so that everything is kind of happy. But there's no phase difference when you tunnel this way. There's only a phase difference when you tunnel this way. And this works. So you can use a Hofstadter butterfly description of all of this as well. It's in here if you care, but I'm not going to talk about it. The transmission in this system, we can identify, this is all simulation for now, we can identify a transmission band which is the clockwise state going around here. What is being shown here is the density of the light as we go around. If we're putting in light here and we're living at this frequency. This has built in the loss in our system. And the reason I'm showing it this way is this is exactly what you're going to see the experimental data, because for the experimental data, we actually just come in from the top and look at our chip, because there's light that gets scattered out of the plane, and that's proportional to however much light is in the chip at that spot. Over here is the counterclockwise, anti-clockwise mode coming around the other way, which looks like that and spectrally resolved. And then in the middle, we get these bulk states that we kind of don't care about, but they live there. And they're not nice looking, so I don't have a nice flat band up here. There's a bunch of nonsense going on. And it looks more like that. So it should work, right? And it does. So all the details are, again, I've covered up the reference, but it shows a bunch of more times. So the chips look like this, and the simulations in the experiment tend to match each other quite nicely. And we see these clockwise and counterclockwise modes, and we've been doing this for a few years now. Okay, I said that these things were robust because they were due to the global properties of the system and not the local properties. What do I mean by that? Well, one thing I mean by that is let's remove one of these links, right? That's a pretty big defect. I mean, I could also just put a defect in there, but what if I just pop one out? It turns out the light will hop around the missing resonator. It won't scatter into the bulk. That was simulation. But here's the experiment. It does the same thing in the experiment. Because, again, unlike in a waveguide, right, this kind of looks like a waveguide. I'm sending light down a direction, but unlike in a proper waveguide, where my guiding is due to some local index of refraction difference between two materials, my guiding is now due to the fact that there are no modes in the bulk for the light to scatter into. So it can't scatter into the bulk because there's nothing there for it to scatter into. It can scatter out of plane. It does a lot of that. That's how we can image it. But it can't scatter into the bulk of the 2D material. There's another sense of robustness to not just to defects, but a spectral robustness. If we look at the bulk states in this system, so we live in that middle band with the bulk, the variation in the actual properties of these bulk states is huge, even as we tune the laser just a little bit. Whereas we saw those edge states, they were kind of 15 gigahertz wide. I guess there was no frequency scale on there, but they were quite wide. And they live on the edge. Not much changes as you change the frequency in those, unlike in the bulk. So there's this kind of sense of robustness, which is really quite nice. So we're doing this in silicon photonics. Why? Because silicon photonics is silicon photonics. CMOS compatible. It's a commercial, foundry process. So we've got these, all of these links on here, and you can't see the shift by eye, obviously, because it's too small. But this is what our systems look like. In fact, this one, that's one array, and that's another array, so we can also play around with making edges between different ones, kind of start back over again. This is approximately what we look like. Like I said, we're imaging the array from the top, and we're just looking at the light that gets scattered out of plane, and this is all at telecom wavelengths. So another nice thing about silicon photonics is we get a tight mode confinement, and it's got a third-order nonlinearity, which means that it can support nonlinear processes, which is another thing that we're interested in here, right? So I haven't said anything quantum yet, and I'm maybe halfway through the talk, so maybe I should talk about something that's quantum. So I think a lot of people in this room would like to do quantum optics on a chip. And if you're going to do quantum optics on a chip, you might want that chip to be silicon because it's a foundry technique, everything's commercial, yada, yada, yada. And if you're going to do quantum optics on a silicon chip, one pathway toward that is doing four-wave mixing in the silicon itself to make single and entangled photon pairs. And this is something certainly plenty of people do. In general, you want to do it in ring resonators because if you want a bright source that makes a lot of photons, you need a fair amount of path length. And the ring resonators, they also give you some control over the spectrum because you only get photons out where the rings are resonant. There's a bit of a problem, though, with that, which is that if I want more photons, I can try and make my ring bigger, or I can make the finesse of my ring higher, but either one of those things reduces the bandwidth. So if I have one ring, there's some kind of a trade-off between brightness and bandwidth, which can be a problem, but people have solved this. I think four-wave mixing was introduced earlier, but I suppose I forgot to say anything about it, just in case anyone's not familiar. In four-wave mixing, we take a bright pump, and two photons from the bright pump get annihilated and converted into two photons that we call signal-annihilar, same as parametric down conversion, except two pump photons instead of one. You have to obey energy matching and phase matching constraints. Energy matching is somewhat obvious. Phase matching is going to be set by the dispersion in our system. So we'll talk a little bit about that later. Sorry, just in case I skipped that. Okay, ring resonators, trade-off between bandwidth and brightness. So people have solved this. What if we just make an array of ring resonators, right? Now the bandwidth is set by the bandwidth of each ring, but the path length, I get a linear increase in the number of resonators. Also, this is the phase matching condition, effectively. in a system like this, and by tuning my pump wavelength, my energy matching condition is effectively a diagonal in here. So by tuning my pump wavelength, I could pick how many modes that I want to make, which is kind of nice too about these things. There's a sense of kind of engineering, the mode number, the separability, and so on and so forth. So this is great. So why don't we just do this? Why am I talking about topological photonics? Well, I've been spending a lot of time telling you topological photonics is robust, and I've been telling you that because this is not. So if I make one of these coupled resonator, whatever, crow waveguides, the problem is that there's fabrication disorder both between devices and within one device. And so if I look at the density of states or the dispersion, these are effectively those two things, in a bunch of different of these devices, there's going to be kind of wild disorder. Each device is going to look a little bit different, and this affects both the energy matching and the phase matching. And so when I do this, we all know that photons are no good to us if we want to do quantum things unless they're identical. And so this is not going to give me identical photons. It's not going to give me photons where I've tried to get my photons out. It's not going to give me photons at my design wavelength, and it's just not going to give me photons that are the same between two devices. And actually, sometimes it's not going to give me photons at all, because if my fabrication disorder is bad enough within a single one of these arrays, just nothing will make it through. So we can see this in the spectrum. So we can do four-wave mixing in one of these linear arrays of waveguides. Remember, this is what the spectrum was supposed to look like. In fact, here, this whole thing is supposed to fit in this box in each of these. It probably wouldn't be resolvable in our case. But instead, in just 3 different devices, we see wildly different spectra. And they don't live where we intend them to live, and they look completely different. And so this wouldn't be very useful for making a bunch of photons to try and use in some quantum information scheme. So now we get back to the topological photonics, right? We have this robust thing, and I didn't say it before, but that robustness extends to the dispersion relation. So these clockwise and counterclockwise edge states, not only are they kind of nice and flat and repeatable because they're due to these global properties, they're robust against these local properties, but their dispersion is nice and linear all the way through the band. Unlike you can see the dispersion here in this bulk band, which is kind of wild and not useful. In here we've got this nice linear dispersion. So we can live and pump here and get our signal and idler on either side. We actually usually do it in different free spectral ranges as opposed to within one, just so we can separate out the signal and idler. And so we get things that look like this. I'm going to show you more of these, but we get our joint spectral amplitude is what we intend it to be. And if we pump in the bulk, we get some nonsense that looks like that. But when we pump in the topologically protected edge states, we really do get, this is simulation, this is data, we really do get light that lives right where it should. So here, I showed you this before. This was the 1D crow. And this is what our 2D system looks like. Maybe I cut one off because those are labeled 2, 3, and 4, aren't they? So we intended for our four-wave mixing to live in this box, and our four-wave mixing lives in this box. And it's the same in all 3. So we do get a big step up. If you want more details, we actually go through a bunch of simulations in the paper with different levels of disorder and talking about what we expect for the identicalness of these sources for the 1D sources versus for the 2D sources. So finally, something else that we have to do is we have to show non-classicality. And we talked a little bit about this before. Okay. We talked a little bit about this before. But we take our photons that come out here, we send them through filters, and then we have 3 SNSPDs that we count them with, and we do 2 measurements. We do a heralded autocorrelation function, a heralded autocorrelation measurement of our signal photon. That is, upon detection of the idler, we look at the autocorrelation of the signal, and we see that it drops to near 0, showing that we do have heralded single photons in the signal arm. And then we also look at our cross correlation between our 2. And I mean, these aren't record numbers, but we have engineered the quantum fluctuations of the vacuum in a topologically protected edge mode in a system, which is, I think, a really neat pathway forward to getting kind of robust single photon sources in a silicon photonics technology. So sorry, I was a little fast. I've reached my conclusions, but I'll take a bunch of questions maybe. So what we've shown is a CMOS-compatible source of single and entangled photons, robust against fabrication defects, this spectral engineering of the vacuum. There are a bunch of other neat things that one can imagine doing in these topological photonics systems. So ours, we did not break time reversal symmetry. We don't have a real magnetic field. The clockwise running mode going this way is the same as the counterclockwise running mode going that way. So it's not a unidirectional device, but there are ways to break time reversal symmetry in topological photonic systems, so you could imagine doing other things like that. And then there's a bunch of other fun stuff that one might imagine doing. We discuss it more in the paper. So these are the guys that I was working with. This is an artist's imagination of what we were doing. Thanks a lot.
Great. Do we have questions for Elizabeth, John, and sorry.
Hey, thank you very much. That was a very interesting talk. What I think I missed, what's the original motivation for using like arrays of rings or like lines of rings instead of just single rings? For sources, I mean.
So you can't make a topological system, if you want a robust edge state, we'll start there. Your system better be at least one more dimension than the state that you want. So if I want a 1D mode, something that guides light and I can propagate in, I better have at least a 2D system, right? You can go down by 2 dimensions. So in fact, there's some work on the archive of one of these 2D chips and then corner states. So you can localize the light at the corners where you go down from 2 dimension to 0. But you always have to work at least 1 dimension above what you want the state to be.
Right, okay, all right, thanks.
We have a question here from...
Great talk. The last data you showed with the devices 2, 3, and 4, all localized to the one box, is really nice. If you were to take, say, a photon from device 2 and interfere it with device 3, what's your expectation for the Hongo-Mandel interference? I
think, I don't want to say anything. I mean, I don't have any reason to believe. It is what it is in a sense, right?
Yeah.
So I don't have any reason to believe it won't just be set by what you can see there, but yeah.
Okay, and what happened to device 1?
I have no idea. This is a really good question.
Thank you.
So what's the minimum and the maximum area you could have for your 2D thing?
So I don't think that, a minimum, I suppose we could kind of make it, each one of these things, here I've got like the dimensions earlier, but each one of these things is the size that it is, and I can only make a circle out of how many of them. The maximum is set kind of by the absorption in the system. Once we propagate too far, we've absorbed and we don't have anything left. I don't think we've made them substantially larger than this. There's a bunch on a chip, but yeah.
I guess towards that point, do you expect to see any superradiance?
Do I expect to see any super? I didn't.
As you increase the number of rings that you're generating photons in, you should see, I think, a quadratic increase in the photon generation rate.
If I'm operating a regime where my probability of generating a photon in any given ring is starting to get big.
Yeah.
Right? So we are not in that regime now. I don't know, can you get into that regime easily?
I think you need good phase coherence between the rings such that the photons generated go into the other ring in some sense.
So we do have that in a sense. We don't need the, right? So unlike with the single mode where it is a problem that they might not make it into the next one, they always make it into the next one here. But so maybe, I don't know.
Okay, thanks.
Yeah.
Is there any other, Stefano?
Thanks a lot for the great talk. So in these protected states, I'm not really, I didn't really understand what you're protecting against. Because it looks like that if you have an imperfection, so like a ring that doesn't work, you still have this edge state.
Yeah.
But then in the end, you talk about the spectral features of the generated photons. So is it something in the so
What's protection?
I don't see how the two are linked in
Sure.
this case.
So there's kind of both protection in both senses. So there's protection in the sense that the light will go around a defect rather than scattering off of it in many cases. There's protection in the sense that the dispersion is also nice and clean and set by this topological. So that was the, where'd it go? Oh, there it is. So the dispersion is nice and linear as well, and that's part of what gives you the nice spectrum. There isn't some, your phase matching isn't going nuts either. Yeah.
Is there a fundamental reason why the two are linked? So why if you expect a spatial kind of protection, then you also get...
Oh, why do you get both? I mean, both are set not by what's happening locally in the material. They're set by the global properties of the material. So, and both are, right? I mean, both the fact that there's no state to scatter into in the bulk and the fact that the dispersion is linear, they're set by these global properties. And so you can push and pull on it to some extent before those global properties start to change. Yeah.
Okay, let's, if there are more questions, probably after the talks, just to run on time. Let's thank Elizabeth again.